As we know, calculus was first invented by Newton and Leibniz to explain the motion of planets and other mathematics involved in nature. And for the most part, what we have been learning can be applied to nature. Therefore, the question now is, how do we apply it? Well, in chapter 4, we learn about the concept of related rate. Let's start with a brief example. Say we have car 1 in a street somewhere driving towards an intersection. Somewhere else in the cross street, we have another car driving away from the intersection. If we draw a line between the cars and ask ourselves, what is the length of this line, say 5 seconds after car 1 started? Or, how fast does the line change? Does it get bigger or smaller? Well, that's related rate. The name, really, already explains the concept. Related rate is pretty much the relation between two rates of two variables in two different functions. We'll come back to the car question afterwards, but for now, let's look at both types of related rate. First, let's imagine a graph, a curvy one with high and low points. This graph is dependent on time, so as time changes, let's call it t, so does the result, f of t. We can obviously find the related rate at any point of this graph, but if we look closely, there are only like 3 ways the graph goes: up, down, or straight. The first case is when the graph goes straight. When the graph goes straight, you see it is always at a high point or a low point. We call this optimization, as we optimize the result to find what we need, either the maximum or minimum amount, depending on our situation. It also just so happens that the rate of change is 0 at these points. We can deduce from this that, at that point, the slope of the tangent line, or the derivative, must also be 0. This will come in handy later in the process. Now, to solve these problems, there are a few general steps to follow to streamline the process. For starters, we need to find the relation equation. This equation should link both variables into one convenient function. But just make sure that the equation has a spot for both variables. When we have said function, we take it and put it in terms of one of its variables. Say, for example, we have an equation like p equals 3n plus u. We will put the equation in terms of n or u. Why? Well, now that we have an equation that defines one of the variables, we can plug it back into the original equation that the question asked for. Say, area equals n times u. If we solve the relation equation for u, we can just replace the u's in the function, and suddenly there's only 2 terms in the original function, p and n. Now, as with everything in calculus, we have to derive at some point. Well, we've hit that point. Derive the equation we just created in terms of whatever variable is not the solution to the relation equation. This is important, let me explain. If the relation equation was p equals 3n plus u and we're looking for the maximum area, what will we derive in terms of p? Always derive for the variable that is on the side that isn't p, or whatever is outside the relation equation. In our case, n was inside. So we take the derivative of a in terms of n. After that, we solve the equation for 0. Now that we have variable and p, we solve for the variable and then we get an equation in terms of p. Since we don't know our n in terms of p and only p, we can then plug it back into our original optimization equation and solve for the other variable. Let's look at an example problem. We'll take this one slow to further understand the concept. The question is, what should be the sides of a rectangle with a fixed parameter to maximize the area? And luckily, we are given the relation equation here. P equals 2x plus 2y. What's our first step? That's right, find the relation equation. With our equation, we put it in terms of one of our variables. Let's pick y. So after some algebra, we end up with y equals p minus 2x all over 2. Now, the equation asks for the maximum area. So our other equation, also known as the optimization equation, is a equals x times y. What do we do next? Well, we know what y is, so we replace y in the area formula for p minus 2x divided by 2. which gives us a equals x times p minus 2x all over 2. We then simplify the equation into a equals x squared minus px over 2. We then have our new equation ready to differentiate. Now remember what I said, differentiate not with p, but with x in this case, since x is more relevant than p. After differentiating, we get dA over dx equals 2x plus p halves. Now, since we're looking for the maximum area based off perimeter, we set the equation to 0 to find the maximum. Well, in reality, even if the equation was looking for a minimum, we'd still set it to 0. The point is to find whatever is relevant to the given question. After solving the equation for 0, we find that x is equal to p over 4. We then plug that back into our equation, and through the magic of algebra, we found that y is also p over 4. So, we know that to achieve the maximum area, the sides must be p over 4 units long. Now, as a quick intermission, you might be thinking, yeah, that's great and all, but how does that relate to the original graph? Well, if you remember, we are in this case only looking for the highest or lowest point, right? So anything that is not high or low, we don't really care about. That's why we set the derivative to 0. Case 2 will explain this in better detail. Let's take another look at the graph. We now know how to find the related rate for the absolute peaks and valleys, but what about the rest? Like, what if we want to find the related rate here, or here? Well, we can do that. In this case, we have to take time into consideration, and most of the equations you get, when graphed with respect to t, will show how the volume, or distance, or whatever changes. But a graph is not enough. We need actual values. Now, to solve a related rate problem like this one, there is no defined method like in optimization. Yet, there are some general things you must follow. First, always start by drawing a picture. This will further help you visualize what you are trying to solve. Obviously, you must find an equation that relates both variables in the picture, but that might not be so easy. In short, look for the one that makes more sense. Like, if it's a right triangle, use the Pythagorean theorem, since wherever you're looking is probably represented by the hypotenuse. After that, differentiate. But not in terms of any of the variables. Instead, differentiate in terms of time. How? Well, use the chain rule. Like, if the equation is y equals n squared, the differentiation would be dy over dt equals 2n dn over dt. Now that you have a differentiated equation, plug in all your given values, rates, speeds, velocities, and all of that sort will be represented by the differentiations, like dy dt or dn dt in the last case. If you can't find the variable, use a relation equation to find it. Again, these types of problems tend to be much harder, yet these are the ones that we can probably better apply to real-life situations. Let's bring back that question from the beginning. Car 1 is in a street somewhere. Let's have it drive away from the intersection this time. Another car is somewhere also driving away from the intersection. Now let's say we are given the speed and distance of each. Car 1 drives at around 20 meters per second and is 300 meters from the intersection. Then we have car 2 at 30 meters per second and it's 400 meters away from the cross section. And let's say that at this time they are 500 meters apart. How do we find the rate at which the distance of separation increases? Let's start by drawing a picture. The sides are going to be x, y, and z, with x being car 1, y being car 2, and z being the distance between them. Since most cross sections in the US and basically in the whole world are right angles, I think it's safe to assume that, in this case, the cross section here forms a right angle. Now, with a picture, let's find the relation equation. Our relation equation here is going to be the Pythagorean theorem, since there is a right angle. Conveniently, we already know all the distances, so our next step is to differentiate. Remember, we need to differentiate based on time. We end up with 2x dx over dt plus 2y dy over dt equals 2z dz over dt. Since we are looking for the rate at which the line changes, our target is dz dt. We continue by plugging in each variable at its corresponding spot in the equation. Ultimately, that gives us 2 times 300 times 20 plus 2 times 400 times 30 plus 2 times 500 times dz dt. Simplify it and we get 12,000 plus 24,000 equals 1,000 dz dt, which can then be further simplified to dz dt equals 36. So now we know that the distance between a car increases at 36 meters per second. Now that we've looked at both types of related rate, let's do some problems to further show off our skills. Let's look at number 19 for an example of optimization. An open-top box was constructed with a 6x6 size rectangular cardboard. What must be the height of the box to maximize the volume? The cardboard is a square with sides 6x6. Let's call the unknown sides x. From the drawing, we would know that all the sides are of the same length. That being said, the length of the open-top cuboid would be 6 minus 2x. The width and the length are of the same values. L equals W equals 6 minus 2x. The height of the cube would be labeled x. The relation equation that we will use for this question is the volume formula for the cuboid. V equals 6 minus 2x, 6 minus 2x times x, which we can then simplify to make it V equals x times 6 minus 2x squared. Then, take the derivative of V with respect to x using the product rule. You will get dv over dx equals 12x squared minus 49x plus 36. Then, carry out optimization at the maximum volume of the cuboid. dv over dx equals 0. So, plug 0 into the equation and factorize to get 0 equals x minus 3 times x minus 1. You will get two answers, which are x equals 3 and x equals 1. But in this case, we will have to reject x equals 3 because x cannot equal 3, since if that were the case, the length and the width of the box would be equal to 0. Therefore, the final answer is x, the height, equals 1 at maximum volume. We will now look at question 2 from the quiz. Let's start with part A. Car A approaches the cross-section with the speed 20 meters per second eastward, and car B goes away from the cross-section with the speed of 10 meters per second north. At the moment when car A is 60 meters away and car B is 80 meters away from the cross-section, how fast does the separation between them change? First, we will draw the positions of cars A and B so we can visualize it better. Since it states that car A approaches the cross-section eastward, that will mean that car A is currently on the west or left side, whereas car B is moving away from the cross-section upwards. We will make the intersection the origin since it is where car A is heading and car B started. The distance between A and the origin is 60 meters when B is 80 meters away. This gives us a right-angled triangle. Let's name the hypotenuse L. To find the length of L, we can use the equation x squared plus y squared equals L squared and plug in the numbers, which would give us L equals 100 meters. This equation, x squared plus y squared equals L squared, will also be our relation equation. Next, we'll take the derivative of this equation with respect to time, denoted by variable t. which gives us 2x dx over dt plus 2y dy over dt equals 2l dl over dt. From the question, we know that dx over dt equals negative 20 meters per second, and that dy over dt equals 10 meters per second. Plugging these numbers as well as x and y and l to get the value of dl dt, which is the rate of change of the separation. Let's now look at part C of question 3. How fast does the angle of sight change from car A to car B? We must first find the relation equation. In this case, it is tangent. We know one side of the triangle is 80 meters and the other side is 60 meters. Therefore, tangent theta equals 80 over 60. This can then be simplified to tangent theta equals 4 over 3. Then, we find the derivative of tangent theta in terms of time, denoted by variable t. You will get secant square theta times d theta over dt equals x times dy over dt minus y times dx over dt all over x squared. Substitute the values into the equation and bring the secant squared theta over to the other side to get d theta dt equals 11 over 50 radians. So the angle of sight from car A to car B changes at the rate of 11 over 50 radians. Let's look at question number 4 from quiz number 3. An inverted cone container with radius 2 meters and height 4 meters is filled with water at the rate of dV over dt equals 2 meters per second. How fast does the water level change when the level is at a quarter of its height? We know this is a related rate problem when the rate of change is not zero, and at the moment when the change of time approaches zero, delta t approaches zero, the function either increases or decreases. We first need to find the relation equation that will join both variables together. According to the question, we want to find how fast the water level changes. We should remember that the volume of a cone is 1/3 times pi times r squared times h. As we know from the question, the radius of the small cone is equal to 1/2 of its height. Therefore, if we replace r for 1/2 h, the volume of the cone is then equal to 1/3 times pi times 1/2 h squared times h. If we simplify it, we can then see the volume is 1 over 12 pi h cubed. The second part of the problem is to find the derivative of the equation. The derivative of volume in respect to time is equal to 3/12 pi h squared times dh over dt. According to the question given that an inverted cone container with radius 2 meters and 4 meters is filled with water at the rate of dV over dt equals 2 meters per second, we can then find that the derivative of volume in respect to time is 2. By calculating, we get the derivative of height to time is equal to pi over 8. Let's look at problem 4 from the homework. Find the area of the largest rectangle ABCD if two vertices are on the line y equals 4 minus 2x and the others on the x and y axes. When the problem asks us to find the maximum, we should remember the steps needed to solve the optimization problems. First of all, the question says that two of the vertices are on the x and y axes. With this information, we can find the 2 points that are on the axis. When x equals 0 in the function, we find our y-intercept is equal to 0, 4. And when y equals 0, our x-intercept is equal to 2, 0. The first step is to find the relation equation. We have side OA equal to x and side OD equal to y. Therefore, if OA is equal to x, AK is then equal to 2 minus x. And if OD is equal to y, DF should be equal to 4 minus y. In the triangle ODA, we can find angle alpha. Angle alpha is equal to 4 halves and also is the same triangle angle. Alpha is equal to y over x. According to this information, we can find that y is equal to 2x. If we say line CB is equal to L, L is then equal to the square root of x squared plus y squared according to this triangle. We find that L is equal to the square root of 5x. On the other hand, in triangle ABK, angle alpha is equal to the angle alpha in the triangle ODA. Therefore, the sine of angle alpha is equal to b over 2x. So, side AB is equal to b, which is then equal to 2 over the square root of 5 times 2 minus x. After simplifying, we find that our relation equation is equal to a equals 4x minus 4x squared. We must then find the differential. After finding that dA dt is equal to 4 minus 8x, we must set the equation to 0 as we know that that is the way to find the maximum of an equation. We find that when 4 minus 8x is equal to 0, x is equal to 1/2. Now that we have the x, we plug it into the original equation to find y. Let's look at the first question from Chapter 4's homework assignment. Find the dimensions of the rectangle of largest area that can be inscribed in an equilateral triangle of side L, if one side of the triangle lies on the base of the rectangle. By reading the question, we know that optimization is needed to solve this problem by the way it asks for the largest area of a rectangle. We first start by drawing a diagram. From the diagram, we can see the rectangle is cut in half by the height of the triangle, therefore making two equally sized small rectangles. The first step, as always, is to find the relation equation. Remember, we must only end up with one variable in the equation. We know that the formula for finding the area of a rectangle is area equals base times height. Since there are two rectangles, the formula of the area is 2xy. In order to get rid of one variable, we need to find the relationship between x and y. We know that with 2 points, we can find the equation of the line. And the triangle gives us the location of 2 points on the line. Therefore, we have the equation of the line, which is y equals negative square root 3x plus the square root of 3 over 2l. We then need to optimize the relation equation. Next, we substitute y into the relation equation we got in step 3. We simplify the relation equation and take the differentiation of the area. Set this equation to 0 to find the maximum area. By doing basic algebra, we get the answer for x. We take that answer and plug it into the equation to find y. Lastly, we plug in y and x into the area of a rectangle and solve for the area. We find that the largest area that can be inscribed in an equilateral triangle of side L is the square root of 3 over 8l squared. In short, for an optimization problem, we must follow 6 steps. Find the relationship between x and y. Find the relation equation and optimization. Substitute y in terms of x into the relation equation. Take the differentiation. Set the differentiation equal to 0 and solve for the variable. Plug the answer for step 5 into the relation equation to get the final answer. For related rate problems, we only have 4 steps. Draw a picture of the physical situation. Write an equation that relates the quantities of interest. Take the derivative with respect to time of both sides of your equation. Remember the chain rule. And finally, solve for the quantity. One last reminder. When the problem is an optimization problem, we need to set the relation equation equal to 0. This is because when the equation is equal to 0, the slope is equal to 0, which means we have found a maximum or a minimum point.